I2C Bus Protocol. The name stands for Inter-Integrated Circuit Bus Protocol. Let us start. Welcome to our channel Engineering and Technology for You. If you are not subscribed, kindly subscribe and press the bell icon to get notifications about our future videos. The topic for today is I2C Bus Protocol. Let us directly start with the introduction. This protocol was developed by Philips Semiconductors. Now presently it is the NXP Semiconductors. Now this is a simple bidirectional two-wire bus for efficient inter-IC control. See, we are developing any embedded system, there are number of ICs such as microcontroller, then LCD, then temperature sensors, and many other ICs are there. So to have communication among these different devices, this protocol was developed. The bus is called inter-IC or I2C bus. Now here the devices which are compatible with this protocol, just simply by an on-chip interface, they can communicate directly with each other via the I2C bus. So this, because of this protocol or the bus, see, it was a problem for the vendors to have communication among the different integrated circuit when designing a digital control circuit. So that problem has been solved with the help of this I2C bus. Then let us see the features of I2C bus. Only two lines are required. One is the serial data line SDA and the other is serial clock line SCL. So these two lines are sufficient for connecting or communicating with the different devices. Now each device connected to the bus has a unique address and will have simple master-slave relationship all the time. So master can operate as master transmitters or as master receivers. Then a true multi-master bus including collision detection and arbitration to prevent data corruption. So this is providing arbitration as well as collision detection. And this will be caused when two or more masters simultaneously initiate data transfer. So the bus will solve this problem also. Then the next feature, 8-bit oriented bidirectional data transfer speeds, say up to 100 kbits per second in standard mode. In fast mode it is 400 kbits. Then in fast mode plus it is 1 mbits, and in high speed mode it is 3.4 mbits per second. So these are the various speeds. It will operate on these various speeds in different modes. Then the 8-bit, if you consider unidirectional data transfer, it can go up to 5 mbits per second in ultra fast mode. Then the on-chip filtering rejects spikes on the bus data line to preserve data integrity. So if the data is getting corrupted because of the spikes, the on-chip filtering, it will reject the spikes so that the data integrity is maintained. Then the number of ICs that can be connected to the same bus is limited only by the maximum bus capacity. So as long as the bus capacitance is less than 400 picofarad, you can connect number of devices to the bus. Then let us go further. Now this is simple example of I2C bus. So here you find microcontroller, then this is the EEPROM and temperature sensor and LCD controller. So there are 4 devices and these are connected by this bus, the 2 lines SDA and SCL. And here all the devices, they are connected to pull-up registers R1 and R2. And this is the power supply. So we'll come to the details of why these pull-up registers are necessary. So general I2C operation. Here we have 2 wires SDA and the SCL, clock and data. So they will carry information between the devices connected to the bus. Now here each of the device, it is having a unique address and it will be recognized by that unique address. So whether it is microcontroller, LCD driver, memory or keyboard interface or ADC, anything, so that will have a unique address and it can either work as a transmitter or receiver depending on the function of the device. For example, the LCD driver will be always a receiver because it's an output device, whereas memory, it can work as transmitter or receiver. And of course the microcontroller, it is a master, can work as transmitter or receiver. Then in addition to transmitter and receivers, devices can also be considered as masters or slaves when performing data transfer. So here generally the microcontroller will be the master. So master is the device which initiates a data transfer on the bus and generates the clock signals to permit that data transfer. So at that time, any device which is addressed is considered as slave. So whenever the master initiates the data transfer with particular address, say for example, if it has the address for the memory, then memory will be considered as slave. Then let us see some of the definitions of I2C bus terminology. Bus is the transmitter, the device which sends the data to the bus, that is, we call it as the transmitter. Then receiver, the device which receives the data is the receiver. Then master. Now here the device which initiates the data transfer, generates clock signal and terminates a transfer, so that we call it as the master. So master can be transmitter or receiver, but it will also initiate the data transfer, generate the clock signals and it will terminate the transfer. And similarly slave. Now slave is a device addressed by the master. Whatever address the device has, according to that address, the master will recognize the slave. Then multi-master. When we have more than one master in the whole system, then they can attempt to control the bus at the same time without corrupting the message. So the I2C bus, it allows us the multi-master mode. Then arbitration. Now this is procedure to ensure that If more than one master simultaneously tries to control the bus, only one is allowed to do so, and uh, the message will not be corrupted. So that is the bus arbitration part. And synchronization. Procedure to synchronize the clock signals of the two or more devices, that is called as the synchronization. So these are the general terms which we'll be using when we are discussing the details. Now let us come to the physical I2C or I2C interface. The physical I2C interface, it has two lines, the serial data line and the serial clock. Now these both lines must be connected to VCC through pull-up registers, and the size of pull-up register is determined by the amount of capacitance on the I2C lines. So maximum capacitance allowed is 400 picofarad. So as long as the total capacitance is less than 400 picofarad, accordingly we'll have to calculate the pull-up resistors so that it does not exceed. Then data transfer master to slave. See, here we are having master and a slave. So data transfer may be initiated only when the bus is idle. So when we consider the bus idle, if both SDA and SCL lines are high after a stop condition, then we call it as the bus idle. So first let us see the general procedure for a master to access a slave device. Say suppose the master wants to send data to slave, then what it will do, first it will send a start condition and the address of the slave receiver. So the address will be 7 bit or 10 bit. Then the master transmitter sends data to slave receiver. Now this data will be 1 byte data, that is 8 bit. And after that the master terminates the transfer with a stop condition. So these are the general steps. The start condition, address, then the data will be sent, and then the termination will be done with the help of the stop condition. Then similarly, if a master wants to receive data from the slave, then in that case the master will be acting as the receiver. So again it will send a start condition and address the slave transmitter. Then after that the master receiver sends the request register to read the slave transmitter. Whatever the register it wants to read from the slave, it will send a request for that. Then the master receiver receives data from the slave transmitter. That means it will receive the address of the register. Then master receiver, from that register it will receive the data from the slave transmitter. Then after that the master receiver will terminate the transfer with the stop condition. So start and stop, these are common. Only here the master receiver is reading the slave register. Then let us see the details of the SDA and the SCL signals. See here the SDA and SCL, these are bidirectional lines, and they are connected to positive supply voltage. So a current source or a pull-up resistor. These are the two possibilities. So when bus is free, both lines are high, and the output stage of the device is connected to the bus. It must be open drain or open collector. If it is depending on the different say families, it will be either open drain or open collector. So in order to perform the wired AND operate AND function, so here you can see in this figure, these are the two lines, serial data and serial clock, and they are connected to say supply voltage with the help of these two pull-up resistor, and then they are connected to different, here we have shown different families, CMOS, NMOS or bipolar, and the VDD, here it is taken as 5 volts, whereas in this case it can be 12 volt or other value. So different voltages can work with the same bus. That is the advantage of using the I2C. Then SDA and SCL logic levels. See, variety of different technology devices, CMOS, NMOS or bipolar, they can be connected to I2C bus. So here logical 0, that is low, and logical 1, that is high, they are not fixed because the voltage will change with the different technology devices. So only we'll have to levels are taken here, 30% and 70% of VDD. So VIL, it will be 0.3 VDD 30%, and VIH will be 0.7 VDD, that is 70%. In this way the things will work. Then data validity. So the data validity on the SDA line is important because the SDA line must be stable during the high period of the clock. Then only the data will be valid. So the high or low state of the data line can only change when the signal clock on the SCL line is low. So you can see here, and one clock pulse is generated for each data bit transmitted, transferred or transmitted. So here you can see this is the clock, which is here it is high and here it is low. Now the data line SDA serial data line, now it is high here. Now during the low period of the clock, change of data is allowed during this. So this can change. So this can go from low to high or high to. That is what is the data validity. And one clock pulse is generated for each data bit transfer. So the clock and data, they are very important in this. Then the start and stop condition. As we have seen, the data transfer begins with the start and ends with the stop. So all the data transfer, they are beginning with the start. This is the start. So start, we call it as a high to low transition. Here you can see the data lines is going from high to low, while the clock is high. That we call it as the start condition. So here this is designated as yes. This part, so the data line going from high to low, and while the clock is, then the reverse of this, when the data line is going from low to high, and again the clock SCL signal is high, so that will define the stop condition. So it is designated by this P. You can see the SDA line is going from low to, and here again the clock is high, so that is defining the stop condition. Now since only this is a 2-wire protocol, so these conditions are very important for the start of the data transfer and the end of the start and stop conditions are always generated by the master. So whenever the data transfer is taking place, the master will generate this condition, and the bus is considered to be busy after the start condition. So after the start condition, then the bus is not idle, it is busy. So bus is considered to be free again a certain time after the stop condition. So the bus will be free here after the stop condition. Bus will be busy during this, in between the start and stop. So this is because this is a multi-master protocol, and then if another master wants to use the bus, then it detect whether it is idle or not. If it is busy, it will not be able to. Then the byte format. See, this is nothing but the data format for the byte, because the data is sent in terms of 8 bits or 1 byte, as we call it as the byte format. So every byte put on the SDA line must be 8 bits long, and it is followed by a acknowledge bit. So data is transferred with the most significant bit first. So MSB is transferred first, and then the LSB will be transferred. The other bits will be transferred. You can see here. Now here this is the serial data line SDA, and this is the serial clock. So we have first the start condition, yes, and in case of repeated start, it is called as the SR. And then we have the MSB, and then here the different data are shown, and then acknowledgement will be there. So after 8 bits of data, we'll have the 9th bit as the acknowledgement. Now if the save cannot receive or transmit another complete byte of data until it has performed some other function, say here clock line held low while interrupts are serviced. So when interrupts are serviced, now this clock line is held low. So when the clock line is held low, then the next start or start condition cannot be achieved, because for the start condition we need the clock line to be. So here when the clock line is low, it will be in the wait state. So that will force the master to be in wait state. Then the data transfer continues when the slave is ready for another byte of data and releases the clock line SCL. So here you can see clock line is released, and as soon as it goes high, again the data transfer can take place. So 1 to up to 8 it will go, and then again it will have the ninth pulse as the acknowledgement. So this is how the format will be there, and at the end of this we'll have the stop condition, or the if it is want to continue the data, it will have the start SR condition, or P condition means stop condition. Then let us go further. Here you see the example of single byte data transfer. You can see the data AA in hexadecimal is shown here. You can see the clock SCL. Now here this will be the period of the clock pulse, and during that the data has to be valid. This is the MSB 1, then we have 0 1, again 0, that is A, and then we have 1 0 1 0, that is again A. So that is how the last is the LSB, and once 8 bits of data are completed, we have the acknowledgement. So acknowledgement is here, the acknowledgement is then let us go further. Acknowledgement, let us see what is how the acknowledgement we are going to get. So each byte of data, including the address byte, is followed by one ACK bit or acknowledgement from the receiver. So the acknowledgement bit allows the receiver to communicate to the transmitter that the byte was successfully received and another byte may be sent. So this is the acknowledgement for the byte. Then before the receiver can send an acknowledgement, the transmitter must release the SDA line. So release the SDA line means the SDA line, if it is say low, it should go high. So to send an acknowledgement bit, receiver shall pull down the SDA line during the low phase of the acknowledge not acknowledge related clock period. So that is period 9. We have just seen the 9th pulse or period is the acknowledgement period. So it will pull down the SDA line so that SDA line is stable low during the high phase of this acknowledge not acknowledge related clock period. So the acknowledge pulse will be low, whereas the not acknowledged pulse will be high. So setup and hold times must be taken into account in order to validate the acknowledgement. So this is the acknowledgement. So it is just during the period 9. If it is low, then we call it as the AC, and if it is high, it is the not acknowledgement. Let us see the not acknowledgement. So when SDA line remains high during the ACK NACK clock period, that is the during this 9. Now here you see, here the SDA line is high, so it is the not or NACK. So when the data is sent, 8-bit data, first the MSB and then LSB, the 9th period will be for the acknowledgement. Here it is high, that's why the NACK is set. If it is held low, pulled down low, then it will be the here no acknowledgement. Then let us go to the slave address and RW bit. Now this is very important because without that you cannot know whether you are going to write the data or read the data. So after the start condition, a slave address is sent. We have already discussed that all the slaves will have a unique address. So this address is 7 bits long and 8 bit is the RW bit. So if it is 0, it will indicate a write or transmission, and if it is 1, it is for the read operation, or it will be the request for the data. So you can see this is the MSB, then the other bits are there, will be there. So that will be the address of the slave, 7 bit, and the 8 bit is the RW bar bit. So it will distinguish between the write or. Then data transfer is always terminated by a stop condition, that is the P. We have already seen this, that is generated by the master. However, if the master still wishes to communicate on the bus, it can generate repeated start condition, SR. So this is what, if the master needs the bus to have more transfer of data, it can go for the SR condition and address another slave without generating the stop condition. So when the master finishes all his work, then only he will generate the stop condition. Otherwise it can generate the start condition called as the SR and again do the data transfer to another slave. So this is the figure which shows the complete data transfer. You can see here the data transfer will start with the start condition, and the start condition we have the serial data line. It is going from high to low. When the serial clock is high, so that is the start condition. And then we have the address, 7-bit address. It will carry the address, it will be carried by the data lines. And then we have the read write bit, RW bit. So if it is 0, then it will be the write operation. If it is 1, it will be the read operation. And then we have the acknowledgement, it will be the 9th bit. And again we have the address, then the RW bit, or if the data is 8 bit, will have the data, all 8 bits data. The 9 bit will be the acknowledgement, again 8 bit data and again acknowledgement. So this is how the complete data transfer will take. And then at the end we have the stop condition. So the stop condition, the SDA line will go from low to high when the SCL is. So this is how, this is the waveform for the complete data. Then let us see how we can transfer data from master to slave on the I2C bus. Now here you see two figures. So to write on the I2C bus, master will send a start condition. So first it will send the start condition, then it will send the slave address, and then it will send the this RW bit. So if it is 0, it is the write operation. So that will determine the operation. So all these are from master to slave up to this. Then the slave will send the acknowledgement, and again the master will send the data. Again it will be 8-bit data, and the 9-bit will be again acknowledgement. Then again it will have 8-bit data, and here we have not acknowledgement, that is A bar is shown, or A, and last is P, that is for the stop condition. So this is how the writing of the data will take place from to the slave. So here in the second figure, we are again writing the data to slave. Here we are just given the details of the address. Okay. First it will start with the start condition, yes, and this is the 7-bit address starting with MSB A6 to A0, and then we have the RW bit, which is 0 in this case. That means we are interested in sending the data to the, then slave will give this acknowledgement. So this will be coming on the SDA line. Then again the master will say register address, so that will be again 8 bits B7 to B0, and again there will be acknowledgement coming from the slave, and again there is a data D7 to D0 from the, and the acknowledgement. So in this way the data will be transferred byte by byte, or in say 8 bits at a time, with the help of the start, stop, and acknowledgement. So then the next part is the reading from the slave on the I2C. Now writing we have seen, it was quite simple. Now reading, here in order to read from the slave, the master must first instruct the slave which register it wishes to read from. It has to give the information which register it wishes to read from. So this is done by master starting off the transmission in similar fashion as the write, by sending the address with the read write bit equal to 0. Now here the read write bit will be 0, signifying write, followed by the register address it wishes to read from. So that is what it will give the information to the slave about the address of the register from which it want to read the data. So once the slave acknowledges this register address, the master will send the start condition again, followed by the slave address with RW bit set to 1. So that is for the read operation. So that will be signifying the read operation. Now this time the slave will acknowledge the read request and the master releases the SDA bus, but will continue supplying the clock to the slave. It will simply supply the clock and the slave will send the data. So during this part of the transaction, master will become the master receiver, because it has to receive the data from the slave, and slave will become the slave transmitter. So slave is transmitting the data and the master is receiving that. So the master will continue sending out the clock pulses, but it will leave the SDA line so that the slave can transmit the data. So at the end of every byte of the data, the master will send acknowledgement to the slave, because since it is a byte oriented protocol, after every byte received, the master will send the acknowledgement to. So once that is sent, the next data will be sent by the. So once the master has received the number of bytes it is expecting, then it will send a not acknowledgements, NACK. So that is indication that the data has been received, and now can halt the communication and release the bus. So once the slave releases the bus, then the master will follow this with the stop condition. This is how the operation will be done. Here the figure shows this things. So you can see this is the gray one is the master control SDA line, and this is the slave control SDA line. So master will send the start first, and then this is the slave address A6 to A0, 7-bit slave address. Then first case the RW bit will be 0, indicating a write. Then slave will send the acknowledgement here in the 9th bit, 9th period or period of the. Then the address will be sent by the master, B0 to B7, that is 8-bit address, and then again that is received by the slave. It will give the acknowledgement. Then here repeated start SR. So again the same address of the slave is given here, and with here RW bit 1. So that is for the read operation. So already it has given the address, register address. So now here the slave will give the acknowledgement for this address, and then it will send the data byte. So this will come on the SDA line. Only the master will supply the clock pulse. Then after this byte D7 to D0 it is received, the master will give the NACK, not acknowledge. So that is given, so that it can, the slave will stop the operation of sending the data, and then it will give the. So in this way you will be able to read the data from the slave on the SQL with only 2 wires, SDA and SCL. So this is how the I2C protocol operates. I hope you have got the things. If you have any queries, you can contact me on Facebook, Twitter, Gmail, Instagram, or you can leave a comment on my website. So since this video was slightly longer. Let us if you like the video, please press the like button and share with your friends, and subscribe to our channel Engineering and Technology for You, and don't forget to press the bell icon so that you get notifications for our future videos. I'll be giving you videos on now how the I2C protocol is implemented using the big microcontroller. Then thanks for watching. Have a nice day.